I have a literal bag of 472 pennies in my room. This is a distribution of the dates on the pennies. I have one penny that was from 1940 that a student gave me about 7 or 8 years ago. The other pennies came from mostly from my husband's dresser drawers when we were first married. That would be this group right here because we were married in 1980. Actually, probably down here. And then other pennies that I've collected over the years. This is the distribution of the population dates of the pennies, and here's the mean penny date, 1989.6. Now, if I were to take a sample of pennies from this bag, we would expect the sample to reflect the population. In past years, my students have taken pennies from the bag, so I'm going to look at some previous year's stuff here. Okay, so here were some samples. Okay, so this was a distribution of a sample of penny dates. So this was 99 pennies sampled from the bag. Notice that the sample of 99 looks very similar to the overall population. The bigger the sample is, the more it's going to look like the population. This is different from a sampling distribution, which doesn't necessarily reflect the population. So remember, we had a distribution of a sample in which each of these X's represents an individual penny date versus a sampling distribution where each individual in the distribution represents a statistic. So now we're going to look at what would happen if we took samples from this distribution of pennies. So what if we took samples of size 2? I'm going to erase some of the stuff that's on here right now. If we took samples of size 2. So notice here that we still see a little bit of left skew. We still see kind of an unusually low value here, but we see more of a clustering of values around the population average of 1989, which is about right here. So we see it's sort of starting to cluster, and it's not quite as skewed as the original population. Then if I do a sample of size 4, notice that the variability has decreased significantly, still centered around 1989, but with a lot more symmetry and a lot less variability. And I'm going to erase some of this stuff because we haven't talked about it yet, so we'll get there. Sort of erase this right now. Now we did a sample of size 9. Notice much less variability than the others and much more unimodal and symmetric looking than what I had before. So we see that in this case, instead of each of these X's representing an individual penny, now each of these X's represents really an X bar, and I probably should have written them as X bars. Each one of these is the mean of a sample of 2 pennies or 4 pennies or 9 pennies. So I probably should make all of these into X bars in all of these distributions. And probably shouldn't take the time to do this while I'm talking to you, but all of these are X bars, not X's. These are means of sample size 4. So this is the distribution of sample means with sample size of 4, distribution of sample means with sample size of 9. Now, what we did is we loaded all of those penny dates into StatCrunch. So now I have penny dates 19, all of my original penny dates, and then we did, see if I can kind of scoot this over so you can see. We did a program here, and I'm not going to go into the details now, but we sampled repeated samples of sample size 5, sample size 20, sample size 40, and computed the mean. So we used the StatCrunch program to do that. And this generated 1,000 samples of size 5 and took the mean of each sample. So these are 1,000 sample means when the sample size was 5, 1,000 sample means when the sample size was 20, and 1,000 sample means when the sample size is 40. So here is a histogram. Let's make a histogram of the original population of penny dates. And I'm going to add the mean here. Okay, so here's what the original population distribution looks like. Very skewed to the left. Okay. Now let's look at the sample means, the distribution of sample means now. And I'm going to put them on one graph with a common scale. So we're going to do a histogram. I'm going to do all three of these. I'm going to mark where the mean is, and I'm going to put them all together on one. Okay, so let's take a look at these. I forgot to put the common scale. Shoot, let me change this. Edit. I want to have a common scale, common x scale. Use same x-axis. Okay, there we go. That's what I wanted to see. Now, notice here in the original that we went all the way from 1940 up to about 2006 for the range. But notice here, this is only 1970, and it's a little less than 2006. This is only between 1980 and less than 2000. And this is probably from about 1985 to about 1995. So notice that the variability of the distribution decreases as the samples, I should say, I'll be a little more specific, the variability of the distribution of sample means decreases as the sample size increases. If I'm doing a sample of individual data values, the variability does not actually decrease with increased sample size. It actually doesn't change at all. It might even increase slightly as you get more extreme values added into your sample. But with a distribution of sample means, the variability decreases as the sample size increases. But notice they're all centered at exactly the same place, the same center as the population has about 1989. So going back here, I also then took the mean, so I need to go to my next page where I was, and let's get rid of this. So here I'm showing the distribution of the sample, the three sample means of size 5, 20, and 40. And now we did some statistics here. We took the mean and standard deviation and the sample size. So my original sample of 472 penny dates has this mean and the standard deviation. The 1,000 means of samples of size 5 has this mean and this standard deviation, and so forth. It turns out that the mean of all the sample means is the population mean, and that looks very reasonable. We can see that with 1,000 samples, we're getting really, really close to that. Remember that a sampling distribution is the distribution of all possible samples of a certain size. 1,000 isn't all possible samples of size 5 that I could draw from 472 pennies. So it's not going to be exactly the population mean, but it should be very close. The other rule that we have about sample means is that just like we had with proportions, the standard deviation of the distribution of sample means is the standard deviation of the population divided by the square root of the sample size. So if I calculate that for each of these using, here's the standard deviation of the population divided by the square root of 5, the square root of 20, and the square root of 40, notice I don't get exactly these three numbers, but I get really close. Once again, because we don't have all possible samples of that size. But notice then that these are very good approximations. For our simulation showed that these are very reasonable numbers. So these would be the actual standard deviations of the distribution of sample means. Now we're going to need to talk then about shape. How do we know when the distribution of sample means could be approximated with a normal model? We don't have the rule of NP and NQ has to be greater than or equal to 10 because there is no P and Q for mean. So we have to have something else to tell us that, which we'll talk about in future videos. But for right now, know that the mean of the sample means is the population mean, and the standard deviation of sample means is sigma, the population mean, or the population standard deviation, divided by the square root of n. And know that as the spread decreases, as the sample size increases, and that we're talking about the spread of the distribution of sample means.